So now that we know a little bit about solubility, we can talk about precipitation reactions. Here we have a picture of a sink from an older home. It's a little dated. But we've got this white crusty stuff on the side of the sink, right? And you get, there's two kinds of buildup that you get on your bathroom fixtures. One of them is really hard water deposits that you have to scrape off with a knife, basically. And then you also get some that are just like this scum, this soap scum. It's that bathtub ring, right? You take a bath and the water drains out, and then there's just like this filmy, sticky stuff on the side of the bathtub. That forms through a reaction of calcium and magnesium ions in the water with the soap that you use to clean yourself. And that actually ends up making the bathtub look dirty. So that it's called a gray curd or bathtub ring. It's just sort of this scummy stuff. Magnesium and calcium are dissolved in tap water. They're not harmful. That's actually good for you. The reason that waters, you buy Evian or 7-Eleven brand or the tap water, they taste different, right? Even though they're all water, because they have things dissolved in them. And it's those dissolved ions that makes water taste good or bad. So tap water is going to have some calcium and magnesium ions. If it has a lot of them, it's called hard water, and if it doesn't have very many, it's called soft water. So hard water has magnesium and calcium. In your laundry detergent, which is, a detergent is different than a soap. Laundry detergents contain sodium carbonate. And the reason they have those is because the carbonate forms an insoluble compound with calcium and with magnesium. And so instead of getting this soap scum on your clothing, the detergent precipitates the calcium and magnesium ions out of solution so that they don't make that curd on your clothing. This is a precipitation reaction. You have two soluble ions, but when they get together, they form an insoluble compound. It's called a precipitation reaction. So we've had a lot of precipitation recently, right? Down here in the valley, it's been raining, precipitation, stuff falling from the sky, right? Up in the mountains, it's been snowing. Snow is also precipitation, so is hail. A precipitation reaction, you mix two things that might be, they'll be clear and maybe even colorless, and it looks like you're making snow. You see this cloudy thing form, and if you wait and watch it, it will fall to the bottom like snow. That's a precipitate. What's happening is you're forming a compound that's not soluble. So in this example, we have potassium iodide. All potassium compounds are soluble, right? So that's going to dissolve in water. And here we have lead nitrate. All nitrate compounds are soluble. And so that's going to dissolve in water. So we have this solution with the potassium iodide, and we have this solution down here with the lead nitrate, and they dissolve very nicely. But when we mix those two solutions together, the lead and the iodide encounter each other. Iodide compounds are generally soluble except with lead, mercury, or silver, right? So this is an exception. So the lead and the iodide ions are going to get together and form a precipitate because this compound is insoluble. So in my chemistry land, what happens with this is potassium is a metal, so potassium's a guy. And iodide is a non-metal, so that's a girl. And so what we've got here is a guy and a girl coming to the party. There's a party in this flask, okay? And so potassium and iodide are coming to the party. Lead and nitrate are already there. And they like each other, Lead and nitrate like each other, but they're not, in a relationship. They're not stuck on each other. So when these guys come and mix with those guys, now lead and iodide meet. And there is a chemical reaction. There's chemistry there, right? They're just like instantly just... You ever been to a party where, like, where's so-and-so? Oh, well, he met a girl and they're on the back porch making out. They're out of circulation, right? They're still there, but they're not circulating. They're not mingling anymore. That's what's happening here. Lead and iodide like each other a lot. And so they form this solid and they're not going to come apart. Well, what about potassium and nitrate? Well, they're just mingling around. They didn't find anyone that they're really stuck on. They're not in a relationship. They're there, they're mingling, they're mixing around, but they didn't precipitate. So we are going to learn how to predict precipitation reactions. What's going to precipitate, what the formulas are. And the way we're going to do this is we're going to look at the ions that are present. So in our original compounds, we had potassium and iodide, we had lead and nitrate. Now those were soluble, they were in solution, so we know that they're not going to precipitate with themselves, right? Because potassium and iodide dissolved in the original solution. When we mix these two solutions, we're going to look at what happens when we potentially switch partners. So we're going to look at what might happen if lead and nitrate get together. What might happen if, potassium and nitrate, lead and iodide. And we're going to look at those combinations. So these are the two possible combinations. And we're going to apply the solubility rules to decide if one of them is going to be insoluble. I was going to say something and it just left my brain. The computer's having an issue too. Precipitation reactions don't always happen. It depends on what the ions are. So here we've got potassium iodide and sodium chloride. So we can write equations for the possible reactants. We could look at what are the ions that are present. There's potassium ion and iodide ion, sodium ion, and chloride ion. And to see if a precipitate forms, we're going to swap the partners and see if they hit it off. Now, these are electrical charges, and so we can't have sodium and potassium getting together, right? Because they're both positive electrical charges, and positive electrical charges repel each other. So we have to have positive with negative. So we could swap the partners and write them with their new potential soulmates and see what's going to happen. So I've just mixed up these pairs. It doesn't matter if I write KCl first or NaI first. It's like adding. 2 plus 3 is 5, and 3 plus 2 is also 5. What does matter is that when I put these two as a pair, I put the metal first and then the non-metal. It's like the Mr. and Mrs. It's just tradition. So I look at these and I say, well, potassium with chloride. And I go through the list of solubility rules. First line, potassium compounds are always soluble. So this is not going to form a precipitate. I go look at this one. Again, first line, sodium compounds always soluble. No precipitate. So the end of this chemical equation is just no reaction. There is no chemical reaction that happened. It's not a chemical change. There was a physical change because these two things mixed. They weren't mixed up before. They're mixed, but there's no chemical reaction. Well, sometimes it's nice to have a list of directions. So this is a list of directions for writing equations for precipitation reactions. Start with the formulas for the two reactants, and then look at how those ions could be paired up differently. Refer to the solubility rules. If any of the possible products, if all the possible products are soluble, then you just write no reaction. If any of them are insoluble, then you need to write the formulas for all the products, put their state symbols, and balance the equation. Let's do some examples. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. So we're going to get some nomenclature practice here too. So these are ionic compounds. We've got ammonium chloride. So I need to write the formulas for the ions with their charges before I can write the formula for the compound. So ammonium ion and chloride ion, and I use their charges to help me put them together. That's NH4Cl. Is that a soluble compound? Yeah, ammonium. So its state symbol here would be aqueous. It's mixed with iron 3 nitrate. Well, iron 3 is Fe 3+. The Roman numeral is the charge. And then nitrate is polyatomic, and you have to memorize that, Fe 3+ and NO3-. So I'm going to write those put together, and because of their charges, it's going to be Fe NO3 3. Is that compound soluble? Second line of that table, nitrate and acetate compounds are soluble with no exceptions. So this is nitrate, it's soluble. So AQ means dissolved in water. It's a little unfortunate that solid and soluble both start with S. Try not to get confused about that. Okay, so now what I'm going to do is I am going to swap the partners and see if there's any chemistry. So I'm going to see what happens when chloride and iron 3 meet, and what ammonium and nitrate do when they get together. So there's ammonium, I'm going to pair that up with nitrate, and then I'm going to pair the iron 3 with chloride. Oops, minus. Before I bother writing the products, the complete ionic formulas, I'm going to ask myself whether these combinations are soluble or insoluble. So ammonium and nitrate, first on the list, ammonium compound's always soluble. So this is soluble. So that would be aqueous. Iron and chloride. So that's down the list a little bit. Iodide, bromide, and chloride compounds are generally soluble except with lead, silver, and mercury. This isn't lead, silver, or mercury. This is also soluble. Is there a chemical reaction? No. There's just mixing. No relationships began at this party. No reaction. Could you write products? You could, but there's no chemical reaction. Yes?
So if they weren't soluble, there would be a reaction?
Yeah. In the next example, we'll see that. So I'm going to do the same thing here when we're mixing sodium hydroxide and copper 2 bromide. Okay, so sodium hydroxide, we need a sodium ion, we need hydroxide ion. Copper 2 bromide, copper 2 is Cu2+, and bromide is Br-. And so we put those together, we get NaOH. That's aqueous, soluble, and copper bromide. Bromide compounds are soluble except with lead, silver, or mercury. This isn't one of those. Went through that kind of quickly because that's just nomenclature. Okay, now we're going to swap partners. It's Br2. Kind of looks like a Z, but there's no reason to put a Z down there. So now I'm going to swap partners and see what happens. I'm going to put sodium with bromide and that copper 2 with hydroxide. And I'm going to go through the list of solubility rules in my head. Well, sodium bromide, sodium compounds are always soluble. So that one's aqueous. And here I've got copper 2 ion and hydroxide ion. And I go through the whole top half of that chart, and neither of these are listed. And I get to the bottom half where things are mostly insoluble, and I see hydroxide compounds are generally insoluble except with calcium, strontium, and barium. This isn't one of those. So this is a solid. This is insoluble. So that means I need to finish. So I'm going to write the formula for sodium bromide and put AQ because it's soluble. For copper 2 and hydroxide, I'm going to have 1 copper ion and 2 hydroxide ions. No charge there. 2. And I'm going to write S because that's a solvent. And then I have to balance the equation. So I have 1 sodium and 1 sodium. I have 1 hydroxide, and over here I have 2 hydroxides. So I need to put a 2 in front of sodium hydroxide. So I have 2 hydroxides here and 2 hydroxides there. But that changed the sodiums. Now I have 2 sodiums and 1 sodium, so I need to put a 2 over here as well. 2 sodiums. Then I have 1 copper and 1 copper. I have 2 bromines and 2 bromines. And there's the equation. Any questions? Yeah.